Here's a typical Newton's law problem that involves the following. This brown object here is actually a piano which is being lowered here. And in order to lower it, there's a rope tied to it and then running upwards that sort of supports the thing from above, and there's a tension in that rope. There's certainly the weight of the piano acting straight down. There is another person holding a rope that's pulling this way with a 500 Newton force, and there's a bit of a horizontal in here you can use for orientation, and that 500 Newton force is being applied at 15 degrees below the horizontal. There's another person pulling on a rope on the right side over here with a force F, which is unknown, but the angular orientation of that one there is known to be 25 degrees. So you sort of have these two angles in there with the forces. So the problem asks the following. They want to know what would this unknown force be if the piano is going to get lowered at a constant speed, and also in that case, what would this tension be in the rope up here? So what is this main supporting tension right here, and what is the tension in this side rope here that two people are using sort of to stabilize the piano as it falls? So it does seem like an intractable problem with maybe even a very difficult way to start, but I claim that one good way to start this is to fall back on what we know. In particular, the x acceleration is the sum of the x forces divided by m, and the y acceleration is the sum of the y forces divided by m. So there's two guiding equations which are the useful forms of Newton's laws which we can use sort of to get the problem started. So there's a couple of bits of information you can sort of glean out of the problem which isn't directly stated. In particular, one is that as the piano gets lowered, no one said anything about it picking up any horizontal motion. In other words, it's never going to start moving left or right. And from that, you can conclude that the x acceleration must be 0. No one says anything about the piano swinging horizontally, so you can assume it won't, so ax must be 0. The next thing you can sort of glean from the problem is that instead about lowering it at constant speed or a steady speed, words like that. So when you hear words like constant v or steady v, these two words also imply that some acceleration is going to be equal to 0. Now, we already have a bit of information about the x acceleration, but since the piano is going to be lowered here, constant v or steady v implies that v sub y is going to be equal to 0, not v sub x. Excuse me, not v sub y will be equal to 0, a sub y is going to be equal to 0. This implies a steady downward speed. So right just from by interpreting the problem, you can pick up two more additional bits of information. That already helps us because in these sides of the equation we see the ay and the ax, both of these can be set equal to 0, so we can get started. So let's start with this x equation here. So if we know a sub x is equal to 0, we can say that 0 then is going to be the sum of the x forces divided by m. And we know this 0 from what we just discussed. So now if I just carry on with this and I just start summing the x forces and divide by m here, well, what are some of the x forces I see on the piano here? Nothing directly, but this force here definitely has a component this way, and this component here is going to be f times the cosine of 25. This one also has a component over this way, and this is going to be 500 times the cosine of 15. Something like that. So there's two x components like that. So what we have then is we have an f times the cosine of 25, and I'm going to call this positive because it's pointing to the right, and we also have a minus 500 times the cosine of 15. I'm calling that negative because it points off to the left. That's the way the Cartesian coordinate system works, and that's my sign convention. So you can see without any real insights into how to start a problem like this, we just used this guiding Newton's law, and I claim we already have an answer in front of us here because this equation here, because this side is equal to 0, can be solved for f. Multiply through by m, and I'll get that f then is equal to something like 500 times the cosine of 15 divided by the cosine of 25. You can put that in your calculator and compute it, but now you know the force this person must be exerting on the piano to lower it at the steady speed given. The next part of the problem then wants to know what this tension is, and because tension is on the y-axis, we probably need to look at the y forces. We have a guiding equation for that. A sub y is the sum of the y forces divided by m, and we know the steady speed a sub y must be equal to 0. So another equation we can set equal to 0, but it does direct our attention to the other coordinate, not the x now. So we can say something like 0 is the sum of the y forces divided by m. And if I go ahead and start filling this sort of stuff in, the very top end, what are some y forces I see? Well, I see t up and I see weight down, so I'll call it a positive t up minus an mg down. Again, I'm using this sort of implied sign convention here that everything up is positive, everything down is negative. That's why I have a minus sign in front of the mg. That's the way the Cartesian coordinate system works. And you cannot forget then about the y components of these two forces here. So this force over here definitely has a y component right there. I won't write it on here because the drawing's getting a little bit crowded, but this is going to be an f times the sine of 25, and it points down also. So I'll label this a minus f times the sine of 25 pointing down like that. And this vector also has a downwards component like this downwards component, it'll be 500 times the sine of 15 to get this component here. So we'll add that on here as well, minus a 500 times the sine of 15, something like that, and all that's divided by m. So what has Newton's law done? Generate us another equation. We know this side's 0 for the reasons that we discussed, so we can just multiply through by m. And so what we'll get from this then is something like t minus mg minus f times the sine of 25 minus 500 times the sine of 15. All that's equal to 0. And you put a big box around that. I'm going to end the video here and end this discussion here because I think you can finish it at this point here. You've generated another big equation for yourself that looks like you can solve for t. And I might say, wait a minute, there's also another unknown F in here, that unknown force that this person was exerting to pull on the piano. But no, it actually isn't unknown. You just found it over here. You can put this into your calculator and get some number for it up here. And whatever number you get is the number that goes in right there. And it looks like you can then solve this equation for t equals something. And that'll give you the tension that must have been exerted up here again to maintain that constant or steady lowering speed, implying all the accelerations are 0.